today. So we're going to go through, I posted these practice problems, but I didn't post an answer key because we're going to work through them in class. So to get the answers for these practice problems, you have to watch the videos. The sheet says chapter 5 and 6. So our next exam is on both chapters, 5 and 6. So all of the examples we'll be doing in class are this packet here. But this week we're just doing chapter 5. Next week we'll look at chapter 6. So let's start by looking at temperature conversions. So chapter 5 is all about heat and temperature. To do temperature conversions, it's not like the chapter 1 conversions where you find a conversion factor, you do that railroad track method, and try to get what cancels, dimensional analysis, all that sort of thing. You're actually using equations. So I give you the equations on the chapter 5 equation and conversion sheet. And the temperatures we're going to be going between are Celsius, Kelvin, and Fahrenheit. So most people have heard of Celsius and Fahrenheit. Fahrenheit's the temperature unit that we use here in the US. Celsius is the temperature unit used everywhere else. And then Kelvin is kind of the new one. So Kelvin is represented by this letter K. My degree signs. And Kelvin is actually the SI unit. So in chapter 1, when we talked about SI units, that was that international system of units that all scientists and mathematicians agreed upon. They're like, these are the units we're going to use, these are the units where we're going to report our data in so that we can share it with each other. So Kelvin is that unit for SI. So with Kelvin, it's the only one out of the 3 that doesn't have a degree sign. And this is because Kelvin is an absolute scale. What that means is you can't have a negative Kelvin. So 0 is the cold, 0K, 0 Kelvin. That is the coldest possible temperature anything will ever reach. At 0 Kelvin, all molecules will cease to move. All life will cease to exist. Everything will be completely frozen. With Celsius and Fahrenheit, it does have a degree sign because it can go negative, right? We can have negative temperatures outside. It can be -5 or -20. I don't think it ever gets that cold here, but it does in the northern states. So since it can be in the negatives, that's why it's degrees. All right, I know this looks like okay, but it's supposed to be 0 Kelvin. So now that we know kind of a little background on the definitions of these units, let's try using these equations to convert between Celsius, Fahrenheit, and Kelvin. So looking at the practice problems, the first one that we were given, 1A, gives us a temperature of -62 degrees Celsius, and it asks us to go to Fahrenheit. So, to do this, you look through your equations and you figure out which one's best to use. So it's kind of like the physics problems that we were doing before. When I am approaching or figuring out what equation to use, you want to pick the one, so for instance, I'm looking for Fahrenheit. So you want to pick the one where Fahrenheit is equal to. So then I want to pick the second one because that way I can take this -62 and I can plug it in where that C is. I won't have to rearrange it at all. This top equation would work, but then I'm going to have to rearrange stuff. And I want to avoid that if I can. So I'm going to pick this one where Fahrenheit is equal to. And I'm just going to take this -62 and I'm going to plug it in where that letter C or that variable C is. So to figure out the degrees Fahrenheit, I'm going to take 1.8 and multiply it by -62, and then I'm going to add 32 to that value to get my degrees Fahrenheit. 1.8 times 62 plus 32. And I get, because I have to round it up, so I get -79.6. I want to keep with the sig figs that I have in the original question. So it's going to be -80. just going to round up with a decimal. And this is Fahrenheit. Now you'll kind of see me relax quite a bit with significant figures as the semester goes on. Some of my answers on the exams even might not be to the correct sig figs. The key is just pick the closest one to what you see on your calculator. All right, so now let's try another one. The next one we have is Kelvin to Fahrenheit. Now, Kelvin to Fahrenheit, this is one of the hardest types, or it is the hardest type of temperature conversion we'll see in this course. Because if you look at our Kelvin equations, we can go between Celsius and Kelvin, but we can't go directly between Kelvin and Fahrenheit. So this is actually a two-stepper. So we have to go from Kelvin to Celsius first, and then we can go from Celsius to Fahrenheit. So we're going to be using two different equations here. I think I also gave you this one as well, the rearranged version, K-minus 273. So to go between Kelvin and Celsius, if I'm looking for Celsius, I want to pick the equation where Celsius is equal to. So I would pick Celsius is equal to Kelvin minus 273. This one down here. Because I know what my Kelvin is, so I can take that 300 Kelvin and plug it in where K is and not have to rearrange. So that's exactly what I'm going to do. I'm going to take this 300 and I'm going to plug it in. So to figure out the Celsius, to get here, I take 300 and I subtract 273 from it. And that's going to get me, I should know how to do this, 27 degrees Celsius. But that's not my final answer. That's just the step to get to Fahrenheit. So next, I need to go from Celsius to Fahrenheit. So Fahrenheit's my question mark. That's what I'm trying to solve for. So when I'm looking at my equations, I'm going to put the equation where Fahrenheit is equal to. So the only equation I have where Fahrenheit is equal to is this second one here. So it's the same one that I used on the last problem. So writing it down, we get 1.8 C plus 32. And where this variable C is, that's where I'm going to plug in that number 27, because that's in degrees Celsius. It's going to look like 1.8 times 27 plus 32. It's oddly strange, we get the same number but without a negative sign. So if we're doing one sig fig, this would be 80. Oh, I wrote degrees Fahrenheit twice, but just for emphasis, I guess. So I wrote 80 instead of 81 because we needed just one sig fig. All right, so if this is the hardest type, these problems aren't too bad, huh? But let's try the last two. Is there two more or just one? The last one, anyway. Because there is still one equation we haven't used, and this is the top one here. We haven't used the equation where Celsius is equal to yet. So, probably guessing by now that's what we're going to use for this one. And you would be right. So in this one, they're giving us Fahrenheit, and they're asking for Celsius. So since they're asking for Celsius, we're using the one where Celsius is equal to. It's rearranged for us. And you're just going to take that 100 degrees, plug it in where the F is. Now the key on this one, so there is a trick to this one because people do often get it wrong for this reason. When they do the 100 minus 32 on the top, they don't put parentheses around it in their calculator. Okay? Okay, and if you forget the parentheses, what it's going to do is, by order of operations, it's going to take 32 and divide it by 1.8. It'll then take whatever the answer is for that and subtract that from 100. And that's going to give you the incorrect answer. So either do the subtraction part first and then divide by 1.8, or put parentheses around that in your calculator so that you aren't having any mistakes just because of calculator error. So this is 38. And I'm supposed to only have one second. That's okay. So if you had a fever of 100 degrees, if you were in Canada, your thermometer wouldn't say 100, it would say 38. Okay, measure in Celsius. Just for a little context. All right. So that is it for temperature conversions. I've used all the equations at least once, so you can kind of see how that looks. The only other thing you really needed to know about temperature was the freezing point and boiling point of water. So know those values. For instance, water freezes at 0 degrees Celsius. So freezing point, FP. 100 degrees Celsius, which is, I'm doing the boiling point, sorry. 0 degrees Celsius, which is 32 degrees Fahrenheit. The boiling point of water is 100 degrees Celsius and 212 degrees Fahrenheit. Another reason why Celsius is kind of nice, it's easier to remember 0 and 100 than these arbitrary Fahrenheit amounts. But most people know that water freezes at 32 degrees Fahrenheit for winter time, because when it gets to be right around 32, that's when you got to look out for the black ice and the icy roads. But the boiling points in Fahrenheit is a little less known. Next time you're making macaroni and cheese or something, stick a thermometer in there, you'll see it is 212 once that water boils. All right, so we're going to move on to the heat now. So the heat portion of Chapter 5 is where our main focus is going to be. We're actually doing a lab using the conservation of heat energy. So the equation for heat, we have two of them. Q is equal to mc delta T, and then Q is equal to mc Tf minus T1. Let's look a little bit at this equation before we use them, just so that we know what these variables mean. Because we need to know what the variables mean in order to read the word problem and figure out where to put what information. So Q, that is heat. So if they say calculate the heat, they're asking you to calculate Q. When we calculate heat, or the Q value, it is measured in calories in this course. Some courses it's measured in kilocalories, some courses it's measured in joules or kilojoules. Well, we're using calories. For M should not be a surprise to you. This is not new. This is mass, just like it always has been. The thing that is new is that we're measuring the mass in grams. So this is throwing you through a little bit of a loop, because the last several chapters, every time we see grams, I've been trying to pound it in your head that you need to get it in kilograms before you put it in the equation. Here's your exception. When you're calculating heat, we don't need kilograms, we need grams. Next variable, C. What C is it's called the specific heat. And this is a value that is dependent upon the type of material that we're talking about. For instance, aluminum has a different specific heat than water. Water has a different specific heat than copper. so on and so forth. So it depends upon the material that you're using. Because specific heat is how much heat that object or that material can absorb before its temperature raises by 1 degree. So for instance, metal, any type of metal, would have a lower specific heat than water. Because if you notice, on a hot day, a metal surface gets a lot hotter than water would. Because it has a lower specific heat, so that metal surface, it doesn't take very much heat for it to raise in temperature. But water does take a lot of heat to raise in temperature. So that's what the specific heats are based on. But to find the value itself, not just the definition, that's also on your equation sheet. So there's this table of specific heats. It gives the substance and then the specific heats off to the right. A lot of times in the problems, I'll put the specific heat in the problem for you, but if I don't, this is where you would find that value on this table. The units on it are weird. No, they're not weird, but the units are given to you on the table, so you don't have to memorize them. And the units are actually helpful in reminding you what the units of your other variables should be. So specific heat is calories per gram times degrees Celsius. So calories, because your heat is measured in calories. Grams, because your mass is measured in grams. And then degrees Celsius is for our last variable, temperature. So temperature, you can guess, is measured in degrees Celsius. Notice we have two equations, and the only thing different is that temperature variable. So up here we have a delta T, and delta T means change in. So this would be if you're given a problem with just one temperature. It's saying this material, this object, had a temperature change of 115 degrees. So you would use this equation. But sometimes they give you two temperatures, and you have to figure out what the change is using this TF minus TI. Because whenever we have change in something, it's always the final minus the initial. So delta T is actually equal to final temperature minus initial temperature. Sometimes they'll give you the delta T, sometimes they'll give you the 2, and you figure out delta T for yourself. And we'll do a problem using both equations, so you can see. So heat is dependent upon the mass, the specific heat or material that it's made of, and the change in temperature. That's one of the concepts that I talk about in the PowerPoints. But you have the PowerPoints to go over that material, so let's do the actual problems. And I have posted some problems on this already as well, but they're different than the ones I'm doing here. So just to give you more opportunities to see them worked. All right, we'll try the problem we have on here first, and then I have another problem that I wrote down that we'll do. So I'm looking at number 2 on the chapter 5 and 6 practice problems. It says calculate the heat released. So I'm going to do my knowns and unknowns like always. So it's saying calculate the heat released. So what heat released means is Q. That's what they're asking for. The heat, the Q value. So calculate the heat released by a 475 gram. So 475 grams. Looking at my variables, that's going to be my mass, my M. And I want it in grams, so I'm going to leave it in grams like they had it. This is a copper pot, and it cools from 47 degrees Celsius down to 18 degrees Celsius. So I have two temperatures that they have given me. Now it's my job to figure out which one is going to be final and which is going to be initial. So I know I'm going to use this heat equation because of the two temperatures. So reading this, it's saying it cools from 47 down to 18. So which one's my final, the 47 or the 18? Where does it end at? 18. So the 18 is my final. It's important to label the initial and final correctly, because if I flipped them, that would be a difference of a negative or positive sign. Because you can have a negative Q value, and you can have a positive Q value. So, looking at this equation, I have my mass, and my TF, and my TI. I don't have the C, the specific heat value. And I said specific heat depends upon the material. So you have to reread and see, okay, what material are they talking about? What is this pot made out of? And it says a copper pot. So that's when you would go to your list of specific heats on your equation sheet and find copper. Following it over, it says that copper's specific heat is 0.094. Now I have all my variables, and I can plug them in. So we have Q is equal to mass first, so 475, times by our specific heat of 0.094. And then we have final minus initial temperature. And we said our final was our 18 minus the 47. So make sure you're doing that subtraction in parentheses. So it can be a negative, so I know my heat value is going to be negative. Times 0.094. We get a very large number. Negative 129. We're looking at 2 sig figs. So it would be negative 1,300. And the units on it are calories. So I'm going to do another one of these that's not on the practice sheet so that we can look at how we use the other type or what the wording looks like for the other type of equation, the other heat equation. So this one is 175 grams of aluminum is heated and the temp increases by 100 degrees Celsius. How much heat is required? So in this case, we have aluminum. 175 grams of aluminum. It's heated, temperature increases, and we're calculating how much heat is required to accomplish this. So let's make our knowns and unknowns list so we can plug it in. What variable is which? We have 175 grams. That's our mass, and remember, for these ones we want it in grams. It's heated and the temp increases. So notice it only gives us one temperature. So that temperature that it's giving us, since there's just one, is our delta. It's saying it increased by a total of 100. It doesn't give us our final or our initial, it just gives us the change. So you see one temp, it's the delta T. Then it's asking how much heat is required. And remember, heat, that's our Q value. So that's our question mark. Since we have just one temperature, we're using this equation. We have the mass, we have the delta T, but the C value wasn't given to us, so we have to look it up based upon the material that is being used. Now, I know I used just the chemical symbol for aluminum. Sorry, that was my shorthand. The word would have been written out for you, in case you don't know the chemical symbol, since we haven't taught chemistry yet. So Al, aluminum, I would look it up, and I see that its specific heat on the table is 0.215 calories, grams, Celsius. Now that I have all my variables, I'm going to plug it into that top equation to solve for heat. My mass was 175. My C value is 0.215. And I'm going to multiply that by my delta T, 100. So this time I'm going to get a positive Q value. And 3762.5. I want 366, it's gonna look like that. Units are calories for our heat. If you want to see some more calculations like this, there's another video doing different ones. But I'll use the same. So there are 2 questions left on the practice problems, and they are concept questions, and we're going to go over those next. So remember, this one wasn't on the practice problems, so we'll write that separate. So I'm looking at number 3 now on the practice problems, and it says the lowest achievable temperature at which all atoms or molecules stop moving is, so this is a temperature question. I actually talked about it at the beginning of this video. I said that Kelvin was an absolute scale, and that 0 Kelvin was the lowest achievable temperature at which all atoms or molecules cease to move. So the answer would be 0K or 0 Kelvin. Notice it also says, give your answer in Fahrenheit, Celsius, and Kelvin. So what that means is we're going to take 0 Kelvin, and we're going to convert it to Celsius, and then we're going to convert it to Fahrenheit. So to convert it to Celsius, we find an equation that has Kelvin in it and Celsius, and we pick the one where Celsius is equal to, since that's what we're trying to solve for. So the equation where Celsius is equal to that has Kelvin in it is the K minus 273 one. I take that 0 and I plug it in where the K is. Celsius, 0 minus 273 gives me negative 273. So negative 273 degrees Celsius is the lowest achievable temperature. Very, very cold. Let's see how cold or how negative that number is in Fahrenheit now. So now, since I'm going between Celsius and Fahrenheit, I find the equation where Fahrenheit is equal to that has Celsius in it as well. So we only have one equation where Fahrenheit is equal to something, and that is 1.8 C plus 32. So we take this negative 273 and plug it in where the C is. Negative 459. So that answers number 3. We did concept and then calculations along with it. So the last problem on the practice worksheet for this chapter says list and define the 3 forms of heat transfer and give an example of each. So when we talked about heat transfer in the PowerPoints, there were 3 types. So the first one was conduction. In conduction, the definition of that was heat transfer. And heat transfer always happens from the hotter object to the colder object, right? You're holding a cup of coffee in your hands. The coffee's hot and it makes your hands feel warmer because of that heat transfer. So conduction is direct contact where heat transfer is occurring. And the example that I just used is an example of conduction. Hot coffee or hot drink, beverage of any sort, warming your hands. So direct contact, and I should also add not moving. So what I mean by that is when you're holding the cup of coffee, there's no fluids in motion, it's direct contact, 2 objects are not moving. There's millions of examples. Now that it's getting colder outside, when you get up in the morning, if you have tile floors or wood floors or linoleum floors, they feel cold to your feet. They make your feet cold because your feet are warm and you're having a transfer of heat from your feet to the floor. Your feet are actually warming up the floor through conduction, through direct contact. Another example, or another type I should say, is convection. Now convection involves fluids. So it's also direct contact, but it's fluids in contact, flowing, moving. So when I say fluids, people automatically think liquid. And yes, liquid is a fluid, but don't forget about gases. Gases can be a fluid too. So this would be liquids, gases. An example, the one I used in the PowerPoint, I think, is when you're heating up water in a pot. So what you have is direct contact between the burner and the pot. That's conduction heat transfer. But the convection transfer is the bottom water, the water closest to the bottom of the pot is getting hot first. But it's mixing with the colder water on top. So these are the liquids, the 2 fluids mixing together, transferring heat, flowing, moving, in direct contact. So that those water molecules transferring heat to make all the water the same temperature, to heat all the water up. Other examples of convection are air conditioning, heat, right? Those are the gases now. You have the air molecules coming in contact with each other and transferring heat. Last but not least, radiation. So the key with radiation is no direct contact. So it's heat transfer without direct contact. Examples, the sun and earth. Right? The sun is not touching the earth, yet we feel its warmth. Okay? If the sun was touching us, bad things. We wouldn't be here. So no direct contact between us and the sun, but you can feel the heat, the warmth of the sun on your face. A fire is the same thing. You don't actually want to touch the fire because that would cause burns, but you can feel the heat of the fire through radiation. Microwaves have radiation as well. That's how it heats up the food. No direct contact there. So a whole bunch of examples. So those are the 3 types. This chapter is going to be very much like the last few. It's not just calculations. You do need to know the definitions and stuff as well. So make sure you're watching those PowerPoints as well as the lecture videos. I will attach these practice problems that we just went over to the video for today for people that are looking at this online. Your next assignment is due on Sunday, and it's just on this stuff that we talked about today and the PowerPoint stuff for Chapter 5. So look at all the Chapter 5 materials in this week's folder to help you do Chapter 5 homework quiz. 15 questions just like always, due by Sunday at midnight. 2 attempts. So if you get any wrong, try it again to get better credit. Mid-semester grades go up today. If you are doing poorly, contact me. We can figure out a plan to get your grade up. There is still plenty of time and plenty of points left to raise your score.